So in this lesson, we will study the concept of parallelograms. Now remember, a parallelogram ABCD is a quadrilateral or a four-gon, a shape with four vertices, for which side AB is parallel to side CD and side AD is parallel to side BC. So take, for example, let's consider this quadrilateral. You can see here that side AB is parallel to side CD and side AD is parallel to side BC. So the quadrilateral ABCD is a parallelogram. However, if I were to distort things a little bit, then of course we no longer have that side AB is parallel to side CD, and of course we no longer have a parallelogram. Okay, so for our first theorem, we'll prove that that opposite sides of a parallelogram must be equal. Now, I will consider the following parallelogram: A, B, C, and D. Then, so we consider the parallelogram A, B, C, D. Clearly, we have by definition, by the definition of parallelogram, we know that AB must be parallel to CD and AD is parallel to BC. Now we want to show that AB is equal to CD and AD is equal to BC. So to this end, we'll draw a diagonal DB. All right. Now, next, we'll consider angle ABD. This angle here. And consider angle CDB. This angle here. All right. So you can observe that since angle ABD and angle CDB are alternate interior angles for lines AB and CD with the transversal, of course, DB. Then angle ABD must be equal to angle CDB. Next, let's consider the angle DBC. So it will be this one here. And angle ADB. Then you can see also that using the same argument, that angle D, so similarly, we can say similarly, angle DBC is equal to angle ADB. Thus, by ASA, so angle side angle. The triangle DAB must be congruent with triangle BCD. AB is equal to CD and AD is equal to CB as desired. Okay, so I will introduce now 3 important results, and I will only prove the last one. Okay, so the first theorem says that in a quadrilateral ABCD, if AB is equal to CD and if AD is equal to BC, then you can conclude that ABCD is a parallelogram. Similarly, in quadrilateral ABCD, suppose that you know that AB is equal to CD, and you know that AB is also parallel to CD. Okay, so maybe a picture here might help. So you have a quadrilateral ABCD. All right, so and you know that AB is equal to, let's say, CD. This A here, and then B. And then you have C here, and then you have D. Okay, and you also know that AB is parallel to CD. Then you can automatically conclude that the quadrilateral ABCD so a picture will probably help here. So suppose you have A and B here, and you have, let's say, C and D here. And you know that AB is equal to CD, and you also know that AB is parallel to CD. Then you can conclude automatically that the quadrilateral ABCD is indeed a parallelogram. And thirdly, we will prove that a quadrilateral is a parallelogram if and only if its diagonal bisect each other. So the condition that the statement that a quadrilateral is a parallelogram is actually equivalent to the statement that the diagonal of a quadrilateral bisect each other. Okay, very good. So let's consider the following quadrilateral of A, B, and C, and D. So we consider the quadrilateral ABCD, where diagonals AC and BD cross. So this is AC and this is BD. And suppose that X is the common midpoint to AC and BD. So have X right here. So in other words, we have that AX is equal to XC and DX is equal to BX. Okay, so AX is equal to XC and BX is equal to DX is equal to BX. Okay. Moreover, we have that angle AXB is equal to angle CXD. So AXB is this angle here. And we have angle CDX. And you can pause here for a second to try to justify why this might hold before I give you the answer. Well, these are equal as opposites, or sometimes your textbook might use the word vertical, hold as opposites of vertical angles. Okay, so if I were to actually rearrange the triangles in a way that is easier for me to read, maybe I have X here, and then I have D here and C, and then I'll have X here and B and A. So this side is equal to that side, right? And this here is equal to XB. Then you can see that these two triangles are congruent to each other. So what I'm trying to say here is that triangle AXB is congruent to the triangle CXD. All right, and this is by appealing to side angle side. Okay, so then we can then say that AB is indeed equal to CD. Okay, so far we have established that AB here is equal to CD. And if you play the same game, you recycle these arguments, you can also prove that. So using a similar argument, or similar reasoning, we can show that this AD is also equal to BC. Try to pause the video for a second and work out the steps for yourself. Let us assume that ABCD is a parallelogram, and we want to show that X bisects the midpoint of the diagonals AC and DB. So let me draw a picture, some picture here. Okay, so call these A, B, C, and D. So we assume that A, B, C, and D is a parallelogram. And we want to show that X, this point here, bisect the midpoints of diagonal AC and DB. So I'm gonna, to make the presentation a little easier to follow, I'm going to introduce some, I'm going to label these angles alpha here and beta, and this one here is mu, and I'll call this one here eta. All right, so now you can see that as alternate angles for lines AB, CD, and transversal AC, alpha must be equal to beta. And similarly, as alternate angles for lines AB and CD and transversal BD, we have that mu is equal to eta. ASA, triangle ABX is congruent to triangle CDX. Maybe to make the correspondence a little easier to see, I can color code things here. So this, this will correspond to that, and this one here will correspond to that. Okay, so you can see here that the triangles ABX is congruent to the triangle CDX by ASA, angle, side, angle, angle, side, angle. Right, and we know that this is true because eta is equal to mu, beta is equal to alpha, and side CD is equal to AB. All right. So consequently, we can then say that AX is indeed equal to CX and DX is equal to XB as desired. Now, a quadrilateral in which all four sides are equal is a parallelogram called a rhombus. Okay, so, and our next result says that given a line segment BC, the locus of all points equidistant from B and C is the perpendicular bisector of the segment. Okay, so let me actually break this down into two parts. I will break our proofs down into two parts. So to prove this result, we need to prove two statements. The first statement is that every point on the perpendicular, and feel free to draw a picture to help you mentally follow my argument. So every point on the perpendicular bisector of BC is indeed equidistant from BC. And secondly, we'll need to prove that every point equidistant from point B and C lies on the perpendicular bisector of BC. So let me draw a picture here. This is B, C, and assume, so for the first fact, assume that AX is the perpendicular bisector of BC. So we cut BC right in the middle here at X. Now, since BX is equal to XC, let me consider this triangle actually. Then by side angle side, the triangle AXC must be congruent to triangle AXB. So the point is, this is a 90-degree angle because it's a perpendicular bisector, right? This is also 90-degree, so they're the same. They share this side. And because AX is a perpendicular bisector, this side must be equal to that side, right? So by appealing to side angle side, then we know that these two triangles are congruent to each other, and we can conclude AB is equal to AC. Now, assume that A is equidistant from B and C. This is B and this is C, and let's say this is A. So in other words, we're saying here that AB is equal to AC. Now we'll draw median AX of the triangle ABC. So X is the midpoint of segment line BC. And since AB is equal to AC, the triangle ABC is an isosceles triangle and as such AX is also is a median and an altitude as well. We've proved this earlier in an earlier lesson. Feel free to pause the video to convince yourself that this is indeed true. Okay, thus AX is perpendicular to BC. As a corollary of the previous fact, we can now establish that the diagonals of rhombus ABCD must indeed be perpendicular. So let me start with a picture. So suppose we have a nice rhombus here. So all sides are equal by definition. Since AB is equal to AD, then A lies on the perpendicular bisector of BD. So if this is BD, then A must lie on the perpendicular bisector of BD. Similarly, since CB is equal to CD, C lies on the perpendicular bisector of BD. But BD only has one perpendicular bisector, right? So that means essentially that therefore AC is a perpendicular bisector of DB, and we can then conclude that AC is perpendicular to BD. Okay, so this gives the desired result.